In this part of the lecture, we will discuss the concept of rings and fields. The concept of ring or a field, it's a highly abstract, modern mathematical concept which is based on the idea of number systems, based on the idea of, for instance, complex numbers. In fact, as we will be getting through this particular set of screens, I encourage you to keep in mind the example of complex numbers as a model for all of the properties we are going to discuss. So the concept of a ring or a field starts from the idea of an arbitrary set of objects of any nature. Now, in order to make such a set of objects a ring or a field, you have to equip this set of objects with two operations, addition and multiplication. The reason we call them addition and multiplication is purely historical and also because the whole thing is modeled from numbers. But for every particular example, these two operations can be anything, well, can be quite different from the addition and multiplication you get used to when you operate with numbers. So speaking formally, this looks like this. We start with two elements, A and B, from this set S. And if you forgot, I remind for you that this symbol flipped over capital letter A, you read it as for any. So for any two elements A and B, you have to be able to add these two elements somehow, and the result you end up with should be another element of this set of object S, and you also have to be able to multiply these two elements. Now, on the top of this requirement that there must be two operations on this set of objects, these two operations must satisfy a few set of rules, or we call them axioms. Again, this set of rules, they are modeled from this fundamental example of complex numbers, so you can keep in mind this example. For instance, the first property we require from these two operations is that if you take A plus B, the result should be the same as B plus A. And similarly, if you multiply two elements, A times B, the result should be the same as B times A. So both operations, the result of both operations should not depend on the order in which you take your elements. This property is called commutativity. So this part it's a commutativity of the plus operation or addition, and this is the commutativity of multiplication. Or we say multiplication is commutative and addition is also commutative. Now the second two operations, the second two axioms or rules the given two operations must satisfy is this one. If you take the combination of A plus B plus another C, and I haven't said that, but C is just another element in my set, the same type of element like A and B. So if you take A, B, and C, three elements, and if you combine them with the plus operation in this order, A plus B plus C, the result should be the same as A plus B plus C, but in the other order, when you do B and C first, and then you add up A on the top of that. The similar identity is required for multiplication, and these two identities they call associativity property of plus and times operation. We also require that there must be a special element, which is called 0. If you forgot this symbol reads exist. So we require that there exists a symbol, element 0 in S, which is defined by one unique property. If you add this 0 to any other element, the result should be A. And that should be true for any element of S. This is, in the language of the higher abstract algebra, this element in fact sometimes called neutral element. 0 is more like a historical conventional name which comes from the model of complex numbers, but in the abstract algebra they call it the neutral element. Similarly, there must be a neutral element for multiplication operation, which is the unity element. And that's the element which possesses the property that if you multiply any other element of your algebra, the result will be the same as the initial element A, and that should be true for any element of S. Both of these call the existence of these two properties. They call the existence of neutral element, or conventionally speaking, existence of zero and the unity. We also require the existence of inverse element. So for any element of S, you require that there must be the negative of this element, and the negative is simply defined by the relation that if you add the element to its negative, the result will be always the neutral element, 0. So that's another axiom you expect from your operation plus, and similarly you expect that for any element in the set S, you could also find the multiplicative inverse of that element, which is the fact that which is defined by the property that if you multiply the element A by this multiplicative inverse, the result will be the identity. In fact, if you look closely at what I just wrote, you will realize there is one missing thing in this axiom. There is one missing thing in this axiom, because if you think of complex numbers, you will realize in the way it is written right now, this axiom does not hold for the complex numbers, because, for instance, the element 0, actually the 0 number in complex numbers, it doesn't have the inverse. So in fact, this is just the reason for that is that this actually it's just a typo. The actual axiom requires that the inverse in arbitrary field, the inverse exists for every element besides 0. So here I should add up that A doesn't equal 0. Let me just move it this way a little bit, and let me put it down like here. So the true axiom of a field sounds like this: for any element of S which doesn't equal 0, there is an inverse with this property. This, of course, calls the existence of negative and inverse, or in the higher algebra abstract language, it calls the existence of additive inverse, so the inverse with respect to the plus operation, and multiplicative inverse, the inverse with respect to the times operation. Now let me just summarize this for you. If you have a set of objects of arbitrary nature and they match all of these axioms, commutativity axiom for both operations, associativity axiom for both operations, existence of neutrals, 0 and identity, unity, and existence of inverses, additive inverse and multiplicative inverse. In this case, you call your set S field, or in fact, sometimes people add up the word commutative field. Right. Now, there is some variation to this construction. For instance, there are fields which do not possess this particular property, which do not possess the commutativity of multiplication only. Normally, all fields we study in algebra, they all possess commutativity of the plus operation. Plus is always commutative, but for many fields, times is not commutative, and in this case, you call your field non-commutative. So you call your field non-commutative field when the property star is not, that's the property star is not satisfied. If, however, the set of objects also fails this requirement, the requirement of the inverse, in this case, the set of objects no longer called field. In this case, we call it just a ring. So ring is the sort of almost a field, so it's something which satisfies all of the axioms beside the existence of multiplicative inverse. So we call it a ring if double star is not satisfied, and the double star is up here. And again, ring may be commutative if your star property is true for that ring, or it may be non-commutative if your star property is not satisfied for that ring. So in this, after I gave you these abstract definitions, it's a very difficult high mathematics, and so please take it lightly. You probably will see more of this in the higher mathematical courses we offer. But we can conclude this slide by saying that complex numbers is a commutative field. Later on, we will study with you another set of objects in this topic, which is called the objects which are matrices, and we will see that matrices can be made into not a field, but into a ring. So, in fact, non-commutative ring. So it will be for the matrices we will build the we will offer some choice for the plus operation, which is really easy actually, and some choice for the times operation, which is far more complicated. But still, we will study these operations on matrices, and we will realize that the matrices are in fact produce a non-commutative ring. So the addition will be commutative. The addition will be commutative, associative. Multiplication will be associative. There will be zero there, very easy element. There will be identity there, not so easy in fact. There will be negatives. There won't be inverses on all occasions. That's why we will call it a ring only, not a field. But sometimes there will be inverses, and we will study how to compute them too.